So today on MotoIQ, we have a very special engine, one that's not modified or supported by the aftermarket very much at all. It's a Nissan MR20 that's out of the current Sentra. Now, we had a request to build a turbocharged one, and I'm going to go through what we did here and some of the limitations of the motor that we had to design things to stay around. One of the first things is the Sentra only comes with a CVT, and the CVT isn't that strong, and adding the torque and power of a turbo would probably smoke it pretty quick. But the Canadian Sentra has a 6-speed, so the transmission and clutch and all that from the Canadian 6-speed Sentra was sourced, and that's what we're going to be using. There's also a Renault that has a helical limited slip diff that can be exchanged in there. So we're going to be running that diff on the car. We don't have those parts here, but that's how we're going to get around the CVT issue. It's going to have a McLeod clutch, like nothing super crazy, but a heavier duty than stock clutch and a light flywheel. Now, some of the challenges we had around the MR engine is, one, it's a direct injection engine, so it's hard to modify the fuel system to get enough fuel capacity for the turbocharger. The other problem is it's an engine designed for fuel economy and really low friction, so there's some things about the engine that make it really weak. Let's start on the engine's bottom end. The first thing is the connecting rods. The connecting rods from the factory are designed to have really low mass and low reciprocating weight. This is for, an economy sort of thing. So these rods are extremely weak. As you can see, the beam is super skinny. The rod bolts are really thin. They're probably like 5/16 rod bolts or something. I didn't measure them, but I mean, you can tell they're really small. And there's no extra meat or anything around. These rods are designed for minimum reciprocating weight and totally to be naturally aspirated. There's not an ounce of material on these that are extra. Another unusual feature is that the small end of the rod is like tapered. I don't know why this taper was put in here. I presume it was for less weight and less friction. It's kind of an interesting feature. Some of the things that I don't like is one of the highest stress parts of the rod is narrow, and there's a big oiling hole up here, which makes it even weaker. One of the other things is that the clearances are relatively wide, and you can actually feel play in here. Normally, you want to have this really close tolerance, almost like a net fit, or else you're going to get some NVH, like it'll make a knocking noise. So this kind of has some play, and I'm not sure why Nissan designed it like this. My theory is to reduce reciprocating weight and maybe some frictional area. But this is not a performance rod at all. Now, the OEM piston is pretty neat. Like it has tapered pin bosses to kind of fit the piston, which is kind of interesting. Interesting design feature. I guess there's like less frictional area at the bottom, but there's more bearing area at the top. Maybe that's something they could have been doing. I'm not sure, but I'm sure Nissan had an engineering reason. They're a lot smarter than me. I just don't know. These pistons have really, really narrow rings. I think they're like 0.8 millimeter when I measured them, and they're DLC coated. So really thin, really low friction, ideal for fuel economy. The oil control ring is really thin. These pistons also use like polymer coating, just like a lot of these features are taken off like our race pistons. As you can see, it has asymmetrical skirts, so wider surface on the thrust side, narrower surface on the non-thrust side, so less friction, but more support where you need it. It's also like a slipper style piston, so it's all cut down, so minimal weight. A lot of features of a racing piston, but it's a hyperprotected cast material, so it's not going to take detonation very well. I mean, one of the things you could see is the number one compression ring is way up on top, so to minimize crevice volume so you don't get emissions. But that makes the number one ring land really weak. Uh, can't take extra cylinder pressure, so the turbo's not going to dig that, and any kind of detonation, it'll probably just break. Kind of like a Subaru engine. Um, it has a pre-chamber because this is a direct injection engine. Um, there's buttresses on the pin boss. That's another cool feature right from racing pistons. I mean, overall, this is a pretty trick stock piston. It's just not exactly appropriate for high power use because of the material and the location of the number one ring. So what we did is we worked with JE Pistons to design our new piston. We incorporated a lot of the OEM features like the pre-chamber. We did reduce the compression ratio. The stock MR compression ratio is about 12 to 1. We reduced it to 11 to 1. There's also some interesting features like the stock piston has zero deck clearance. Now I think they're doing this to get the maximum quench and to reduce crevice volume for emissions to the absolute minimum. But if you get any piston rock about top dead center or if anything gets slightly out of kilter, you could hit the cylinder head. Like if you have a little bit bigger piston wall clearance for a forged piston, more rock, you could start burnishing that. So we designed these pistons to sit about 10 thou below the deck. This is like typical on older engines. This allows us to refinish the deck if we have to true things up. It also gives us a little bit of clearance for rock. We kind of like that. It's more performance oriented. When you look at our piston, one of the first things you can see is we moved the number one compression ring down, so you have more material here, so you're less likely to bend the number one ringland and pinch a ring. We added a pressure equalization groove. We're running low tension thin rings, but not as thin as stock. We have an asymmetrical skirt like a lot of our builds do, so wider on the thrust side, narrower on the non-thrust side. Kind of like the stock piston, but maybe a little bit more extreme. We have an offset piston pin. Now we offset the pin to the thrust side, so when you're coming up to TDC and your power stroke starts, you kind of lay the piston in there a lot smoother. That helps reduce like any kind of piston rattle and knocking noise. That's kind of important because of the material we used. We're running a 2618 as our forging material, and that's a low alloy or low silicon alloy. So it's tough, it's ductile, it's stronger. Maybe it's only a disadvantage is it's a little bit less abrasion resistance, so your ring grooves don't last as long, and you got to run a little bit more piston to wall clearance because it expands more. But it's stronger, and detonation's not going to hurt as easily. We did a J's ceramic thermal barrier coating on the top, anti-friction polymer side skirts. Overall, it's a pretty trick piston. Pretty proud of this sucker. I mean, direct injection can be tricky. You have to maintain the top geometry, so the direct injector creates its right charge stratification near the spark plug and everything, and we try to accommodate those design features but still have a performance piston. So the piston should be, in fact, the piston is a lot stronger, lower compression, more suited to turbocharging. Now, when we talk about pistons, we can also talk about the rings. So these rings are your typical performance ring. Number one compression ring is nitrided, and it's PVD coated on the friction face. It's low friction, pretty tough, can conform to the cylinders. It's not as skinny as the stock rings, but this thing will have some durability. The number 2 ring is like iron with a Napier profile. Napier profile means that there's a little hook in the side contour. That hook is really good to scrape oil that gets past the oil rings off the cylinder walls. It's also a thin edge that conforms to the cylinder and breaks in real quick and gives you your ring seal right away when you first start your motor. Um, we have a really thin, low tension oil ring. It's typical for performance pistons nowadays. It used to be like cutting edge stuff, but now just about all the performance pistons from the big guys come that way. For the connecting rods, we went with Carrillo. Because they can quickly make rods custom to any spec. Now, nobody really makes rods for these MR engines, so we had to come up with a custom rod. Um, as you can see, it's a ton beefier than the stock rod. Like this stock rod was designed for the stock output of the MR engine and not a bit more, but this Carrillo is a lot stronger. Now, the Carrillo rod is a beam type rod. It's machined from a near net shape forging, so you get the good grain flow going around. I believe the alloy is like it's Carrillo's proprietary alloy, but it's something like a 4340 family, so it's like a high nickel, high chromium alloy. This is a tough rod that can take impact force, and it also has good tensile strength. Carrillo also makes their own rod bolts. Like the industry standard is generally ARP 2000, but Carrillo makes their own proprietary bolt in-house, and it's really high strength. Carrillo is kind of like the industry standard of the top high-end rod. So you find Carrillos in anything from sports bikes to F1 cars. They are a little bit spendy, but they're worth every bit. When you look at them, there's a lot of details. Like there are absolutely no sharp edges anywhere on the rod that can start like a stress riser. There's a little bit of a rib in there. What Carrillo's found through their FEA analysis is this rib actually contributes quite a bit to strength. I don't know what the exact amount is, but it helps, and it really doesn't add any weight, and it's kind of a subtle design feature. The rods are polished after they're machined, and then they're given the 2-stage shot peening with like a really big shot and then a small shot to get a really good compressed skin. Like this kind of shot peening will improve the fatigue strength of at least 100%. It's kind of like a hard surface that cracks can't propagate in, so that's why the fatigue life gets so much better. They're also super precisely machined, and they're all come just about balanced, so you don't really need to balance them. We specified ours with a bronze bushing for the small end, and we asked for the clearance to be really tight to help with NVH. These are some of the best rods you can buy. I wouldn't hesitate to use them in anything, and most high-end racers actually do use Carrillo. For bearings, there's not much for performance bearings. Like we did try a few, but we couldn't get the right main clearance, so we ended up using the stock bearings. We're probably going to WPC treat them to try to bring them up a little bit. Typically with the WPC bearings, their load bearing capacity goes up by 20%, so we think that'll help out a lot. But currently we're using the genuine Nissan bearings so we can control oil clearance better. So with our pistons, we're running JE's piston pin. Now this is like a chromoly pin, heat treated. It's really close tolerance, so it's close to net fit into the Carrillo rod, so we're not going to have knock or anything. It's about the same wall thickness as the OEM pin, but it's a higher grade material. It also has a chamfer on it, which helps positively engage the wire ring locks. Now this chamfer is really important because if the pin starts to come sideways and get out of there, this chamfer actually wedges the lock into the piston tighter. So important design feature. Like you should probably use the piston pins that your piston manufacturer recommends, and that's what we're doing. It also has a honed interior instead of just drilled, so it's nice and smooth, so there's no stress risers that can develop in there and less places where it can fail. And overall, it's a higher quality part. The crankshaft is one of the major points of the engine that's actually going to hold it back a lot. Now, this engine was built for fuel economy and responsiveness, not necessarily built for power. It's also built to have a wide power band to work with a CVT tranny. It wasn't designed for performance, so the crank is designed to have minimal mass, low reciprocating weight, and I don't know, be economical, I suppose. So smaller bearings, less friction, better fuel economy. Now, none of this is good to make power. So when you look at the crank, the journals are very small, and there's no journal overlap. So when we talk about journal overlap, you probably, if you watch a lot of our videos, it's the amount that the journals actually overlap. And the more the journals overlap, it makes a significant difference in the crank strength. Now this crank has almost no journal overlap, and everything is like kind of small. The journals are small, so there's not much bearing area. There's not much meat to make this strong or rigid. It's not fully counterweighted. So this is probably the weak point of the engine. So because of this crank, we're limiting the horsepower of this engine to probably about 280 horsepower, but that's still quite a bit more than stock. But if you really wanted to develop one of these engines, you would probably need to do a custom crank, fully counterweighted. We'd probably specify it to use like a Honda K series rod bearings and make a custom rod with a Honda K series big end. But that probably adds about $5,000 to the cost of the build, and we just wanted something to make a little bit of power and not like overwhelm the transmissions available and things like that. I mean, it'd be nice to make 400 or 500 horsepower, but then when you blow up all the trannies that made it to the engine, that's not so great. So we're going to see what we can get away with the stock crank, and we feel that the limit is going to be about 280 and still be really reliable. I guess we can talk about the turbo system. CCS Customs helped us out with this. Zach over there helped us adapt the stock manifold so we can use state-of-the-art Garrett turbo. Now this is a G25 550. It's the small G series, but this sucker can make 400 horsepower pretty easy, even though it's in the small T25 envelope. Probably a lot of you know about the Disco Potato and the Disco Potato Turbo and how that was designed as a quick responding turbo that's like the ultimate for like a streetable 2-liter. Well, the G series is like a Disco Potato on steroids. It has a lighter rotating system. It's more efficient. It's actually quite a bit more efficient on the compressor and the turbo side. And it's like the Disco Potato, it's like ball bearing. So think of this as a Disco Potato on steroids. It's smaller, but it flows more air, and it'll spool faster, and it'll make more power. We adapted it to fit the stock manifold, with a V-band here. This is what you call a Cobra head. The frame rail is like right here, and there's not that much room for a 90-degree elbow. So the Cobra head is like a really tight elbow, but it has this flare, so you don't lose that much flow when you got to do a tight turn. We also made like a downpipe. It all packages very nicely. Like when you put everything in there, you can barely tell that the engine has a turbo on it. So really good packaging. The turbocharger was actually the simple part of the deal. This being a direct injection motor, fueling it is quite a problem. The direct injection motors have like really high pressure injectors. There's not a lot of aftermarket on them. There's a high pressure pump. You see about 2,000 psi pressure. So it's not something that you could add fuel with that much. And since we're turbocharging, we're adding a significant amount of power. I mean, we need a significant jump in fuel. So normally you would add additional injectors and control them. So you would kind of turn it into a port injection, direct injection setup, kind of like what Toyotas have. But one of the problems with the MR is it has a plastic intake manifold, so you can't just weld injector bosses on there. So Jim Wolf Technology came to our rescue, and they developed this spacer that goes between the cylinder head and the stock manifold, and holds 4 additional injectors, 1 per cylinder. They also came up with this fuel rail. It uses Bosch EV14 Motorsports injectors. It all fits really nice and tidy in there. It taps off the low pressure lift pump. So the low pressure lift pump produces about the same amount of pressure that most port injection systems make. It's a real nice, clean installation. Once it's on the motor, you can hardly tell it's there. It's a great thing. Jim Wolf made this as a custom one-off for us. It uses the OEM O-rings to seal. It's really nice. Now, if you wanted to duplicate this engine, you could probably call them up, and they'll probably make you one, because they have all the CAD files on this, but it's not something they stock. But they have all the stuff, and they know how to make it. They'll probably make one for you if you are willing to pay for it. For camshafts, nobody makes a camshaft for this engine, so we're running the stock cams, which is fine for the power level that we're trying to get. Like, the power we're going to develop is well within the capability of the turbo. The turbo can even make quite a bit more power, but the crank's not going to take it. So, and maybe the transmission won't either. So why, complicate things? So we're running the stock cams. The cylinder head was a little bit interesting. The valve seats had this weird hump in them that kind of choked the whole opening of the valve right below the valve seat. Now, I can't figure out why Nissan put that hump in the valve seat. I kind of think that maybe it contributes to like tumble. So as the pistons come down from TDC, like you get a tumble turbulence that maybe sits and spins around in this pre-chamber in the piston, and the direct injector is shooting right into there, so it has like a stratified charge. It might have something to do with that, but I think that really is a huge detriment to performance and flow. So what we did is we very carefully ported that out, so it's kind of a smoother transition. And there was like a big lip from the port into the valve seat too. So we kind of smoothly took that out. Like, we didn't really port it because to make only 280 horsepower, we don't need it. But we got rid of the hump. We did our new in valve job, so it's kind of like a smooth radius. But we didn't go too crazy about unshrouding or doing anything around the chamber side, because a lot of that shape could possibly be features that the direct injection works better with, and we didn't want to mess any of that up. It's not a development engine, so we just are kind of playing it safe, and we don't have to make that much power. So that's what we did. We just kind of cleaned up that area right under the valve, but I still think it's going to make a huge power difference, because that restrictor ring in the seat has got to be bad for power and low lift flow. The rest of the valve train is pretty stock. I mean, we have select fit, super lightweight, DLC coated cam followers, but that's stock. We have pretty good stock valves. They're nitrided, and they have sodium filled stems to conduct heat out of the valve face. And believe it or not, that actually gives a little bit of margin on the tuning. The valves aren't hot, the exhaust valves aren't hot, and they're not a nucleus of detonation. So in the tune, if somebody has sodium valves, usually you can see a difference. So we're using the stock sodium-filled like exhaust valves anyway. For the valve springs, we're running the higher tension springs from a Juke 1600cc turbo engine. Now these are a direct replacement for the 2-liter engine. The interesting thing is that they have about twice the tension. They have twice the tension on the exhaust side and something like 25% more in the intake. This is there to help prevent valve float a little bit from the valves having to work against the boost pressure. But we think a big thing is to improve thermal conductivity and to get heat out of the exhaust valve. If you have more seat pressure, believe it or not, your thermal conductivity goes up quite a bit. That's kind of hard to wrap your head around, but there's like engineering white papers on the effect of seat pressure on thermal conductivity, so it's a real thing. So head's pretty stock, cams are stock, the rest of the valve train's stock except for the MR16 turbo valve springs. The block is a lightweight aluminum die-cast part. It's not really built for strength. It's built for lightweight, for fuel economy and stuff like that. One of the things I don't like is the main caps are very wimpy and they don't have much register area. That's one of the reasons why that I want to hold the power down to about 280 wheel horsepower. At least the caps are made out of iron, but they're pretty small and pretty unsubstantial, almost like a 4AG or something. They also have pretty small bolts. These are torque to yield bolts, so we replace them with brand new ones. This engine does have oil squirters for the cylinder walls, which is a good feature for a turbo engine. It squirts the bottom of the piston dome, keeps the dome cooler, and also helps lubricate the piston pin and the cylinder walls. So you can see the provisions for the squirters here. And that came from the Nissan factory like that. It's probably because this thing runs a really high compression ratio with direct injection and all that. So probably needs the piston squirters to help keep the piston dome cool, especially that cast one. This fitting here is oil feed for the turbo. Some of the things that aren't too performance oriented are it's an open deck block, so we got to be careful not to lean on it too hard. There's not much area for the clamp for the head gasket, as you can see. Like the water jackets are huge. This isn't too good for sealing, so it's another reason not to lean on this engine too hard. Also, the head bolts are fairly small diameter, so we can't really lean on them too much. We had to build this engine pretty quickly, so we didn't try to source studs or anything. We're just running brand new torque to yield stock bolts. Now the piston cylinder wall finish on this is pretty interesting. This engine, Nissan uses a torque plate to machine it from the factory, so the bores seem a little off when there's no torque plate. But the bores were in really good shape, so we went to standard bore pistons. We didn't want to use a stone hone because that would make the cylinder walls round, and then with the head bolted on, the distortion would be all off, and we didn't have a torque plate, and we're not going to make one because I don't think there's going to be too much interest in building these MRs. So what we did do is the stock bore finish is really smooth. Because the stock rings are DLC coated, they need a super smooth bore. So it's almost like the bores were like glass or like chrome plated. Like there was no crosshatch that you could see with the naked eye. They're like shiny, polished almost. And our rings wouldn't seat with that, so we had to create our own crosshatch pattern. Like I said, because this is a torque plate engine, we couldn't use stones because it would make it round with no torque on there. We wanted to maintain the factory bore size. So what we did is we used 2 different flex hones. We used about a 480 to roughen up the cylinder walls, and then we honed it with a levigated alumina flex hone, and that knocked the tops off to give it a plateau, nice finish. With a turbo motor, for better ring life and better piston skirt life, you want the crosshatch to retain some oil in it. And that ultra smooth one, that, like the OEM finish, that wasn't going to retain any oil hardly. So this crosshatch will have just enough oil to keep the rings happy and keep everything well lubricated, but it's still actually really darn smooth, so it's going to be low friction. So we had to change the cylinder wall finish to suit our piston rings. Everything else is pretty much stock. This engine runs like a really thin head gasket. I think I measured it 15 thousandths or something, super thin, like almost one layer of an MLS head gasket. So this surface has to be really smooth, like like hand lapped. Get every bit of unevenness out of there so it seals up. And basically that's it. This MR engine can't take a lot of power without spending a lot of money. I suppose you can get 400 or 500 horsepower out of it if you wanted to spend a bunch of money. I mean, what we do is probably CNC machine this, make it a closed deck. We'd build a bottom end stud girdle. So we'd make a girdle that probably bolts to the pan rails and bolts over the main caps and ties everything together. We would probably have Sonny Bryant or somebody to build us a crank, and we'd use Honda K-Series big end diameter bearings. And this probably could hold 400 or 500 horsepower, but it would be big bucks, and we're not sure if anyone out there is going to spend that much. So that's about it. We'll see what our MR makes, and we hope that after the customer's run it for a while, he brings it back and we can take it apart and examine it and really find out what this engine's strengths and what their weak points are, and we can get more expertise on building them. So, we've never had a call on this. Is the only one that anybody ever wanted to do, but I guess if you wanted to duplicate this, give us a call. I don't know how well it's going to hold up yet. Like I said, I think if it's held to below 280 horsepower and below, it's going to do fine, but it's not going to be a big power motor. But you know what? 280 is like double the stock power, so probably more than double, because that's 280 to the wheels. So I think it'll be pretty fun, especially compared to stock, and the turbo system and everything packages real nicely. So if you're interested, go to MotoIQ.com, hit Garage Services. If you have any weird engine development program for the right price, we'll take it on. I think we're pretty good at that kind of stuff. If you like our content, please subscribe. You can comment. We'll try to answer it. Go to MotoIQ.com. There's thousands of tech articles there for many years. You'll probably enjoy them if you're any kind of gearhead. If you want us to build your engine, click on the Garage Services link, fill it out, and we'll get back to you. We also have a web store. We have all kinds of parts, all kinds of engine parts, suspension parts. Go to our web store, buy parts from there, help support us. If you like the shirt I'm wearing, we have our own line of merch, so please buy that. So I hope you enjoyed this video, and next time we'll talk to you about more automotive tech. See you later.